Right, today's set of notes is bond enthalpies and covalent bond strength. As always, you've been given a set of notes, or you can use the ones in Schoology and put them in Notability. So by definition, the strength of a bond is the energy that it's required to break that bond. Okay, and the name that we give to that is bond enthalpy. Okay, so for example, the bond enthalpy of the chlorine-chlorine bond is measured to be 242 kilojoules per mole. That is the energy that is required to break that bond. Okay, it is a positive value. Okay, so positive delta H because it requires energy put in, and energy put in, of course, is endothermic. Okay. When we talk about bond enthalpies, we typically talk about average bond enthalpies because for most covalent bonds it's an average because it'll change slightly from compound to compound depending upon what other things that bond is bonded to in other areas. For example, if we have the carbon-hydrogen bonds in methane, CH4, right, CH4, okay, that's going to be slightly different than CHCl3. Why? Well, here you've got hydrogen bonds, you've got hydrogens bonded, and this is all non-polar covalent bonding over here. Whereas over here, with the chlorines bonded to the carbon, those are all going to be polar bonds, which means that electrons are all going toward the chlorines, which means that this is going to be a little bit more polar in this direction, and that disrupts the amount of energy that's required to break that bond in one versus the other. So if you took the average of all of the different chemical compounds that you possibly could that have a CH bond and you average them together, you get a value of 413 kilojoules per mole. So it's an average bond enthalpy. Where that bond enthalpy occurs has to do with Coulomb's law again. Okay, so we're talking about the charges of the particles within the atom. So protons and electrons are positives and negatives, nucleus and electrons, as well as distance. Okay, so bonding in a covalent bond happens at an energy minimum. So you lower the energy by getting a better electron configuration for them coming together, right? What do I mean by a better electron configuration? You're moving more towards the octet rule, okay? And by doing that, you're filling sublevels, which, again, creates a lower, if you're filling S&P sublevels, which creates a lower overall energy, okay? So you lower the energy if you start to pull them, get them closer together, because you're creating octets, filling S and P orbitals. But you also have a problem where you end up with higher energy from repulsion, because if you get them too close to one another, the nuclei of both begin to repel one another, as well as electrons that are now in super close proximity. So in the end, what you need is a just right moment, okay? If they're too far away, you can't take advantage of lowering the energy from creating the octet. If they're too close together, the energy goes way up because of all the repulsive forces. So somewhere in the middle, you end up with a minimum, which is where we record the bond length at, or the bond enthalpy. Okay. All right, so as a consequence of that, the length of the bond also is something that tells us something about the strength of it. Shorter bonds are stronger. The atoms are closer to one another. They're holding on more. Longer bonds are weaker because the atoms are further away. So by Coulomb's law, the attraction is not as good. That means that shorter bonds have greater enthalpies. Okay, if they're stronger, it takes more energy to break them. Longer bonds are weaker. They have lower enthalpies. Why? Because it takes less energy to break them. This is all, again, based on Coulomb's law. Super short set of notes. That's all there is for that.